Welcome to the world of electrolytic cells, where electricity drives chemistry. In this presentation, we explore how an external voltage can force non-spontaneous reactions to occur. We cover the components of an electrolytic cell, the difference between electrolytic and galvanic cells, the electrolysis of molten salts and aqueous solutions, Faraday's quantitative laws, and real-world applications. Master 5 quizzes and 5 worked problems to solidify your understanding. An electrolytic cell is an electrochemical device that uses electrical energy from an external DC source to drive a non-spontaneous chemical reaction. The process is called electrolysis. From the Greek words electron meaning amber, associated with electricity, and lysis meaning dissolution or to break up. Every electrolytic cell has 4 essential components: an electrolyte containing mobile ions, 2 electrodes, anode and cathode, and an external power source. The electrolyte may be a molten salt, an aqueous solution, or even an ion-conducting polymer. A direct current is passed through the electrolyte. Positively charged cations migrate toward the negative cathode, where they gain electrons and are reduced. Negatively charged anions migrate toward the positive anode, where they lose electrons and are oxidized. The overall reaction is non-spontaneous, meaning the Gibbs free energy change delta G is positive. The decomposition potential is the minimum voltage needed. Any extra voltage beyond this is called overpotential, which is especially significant for gas-evolving reactions. When solid sodium chloride is heated above its melting point of 801 degrees Celsius, the ions become mobile. Applying a voltage across inert electrodes produces sodium metal at the cathode and chlorine gas at the anode. The overall reaction is 2NaCl. Liquid yields 2Na liquid plus Cl2 gas. This process is carried out industrially in the downcell at about 580 degrees Celsius, using a eutectic mixture of NaCl and CaCl2 to lower the melting point. A steel mesh diaphragm separates the reactive sodium from chlorine. In aqueous solutions, water competes with the dissolved ions for reaction at the electrodes. The selective discharge rules determine which species reacts at each electrode. At the cathode, metal ions with a reduction potential above negative 0.83 volts are deposited. Those with lower reduction potentials lose to water reduction, producing hydrogen gas. At the anode, halide ions are oxidized to halogens, while oxygen-containing anions like sulfate and nitrate lose to water oxidation, producing oxygen gas. Classic examples include electrolysis of water producing hydrogen and oxygen, and electrolysis of brine producing chlorine, hydrogen, and sodium hydroxide. The same physical electrochemical cell can operate in either mode, depending on the applied voltage. In a galvanic cell, a spontaneous redox reaction produces electricity, and delta G is negative. In an electrolytic cell, electricity drives a non-spontaneous reaction, and delta G is positive. The sign conventions differ. In a galvanic cell, the cathode is positive and the anode is negative. In an electrolytic cell, the cathode is negative and the anode is positive. But electrons always flow from anode to cathode in the external circuit in both cell types. Michael Faraday published his 2 quantitative laws in 1834. The first law states that the mass of a substance liberated at an electrode is proportional to the quantity of electricity passed. The second law states that for the same charge, different substances are liberated in proportion to their equivalent weights. The combined equation is m equals I times T times m divided by F times V, where F is the Faraday constant, 96,485 coulombs per mole. That is the charge of 1 mole of electrons. It is the product of Avogadro's number and the elementary charge. Electrolysis has transformed industry. Electroplating deposits thin metal layers for decoration and protection, such as chromium on car bumpers, gold on jewelry, silver on cutlery. Electrorefining produces 99.99% pure copper from impure anodes. Precious metals like gold and platinum collect as anode sludge. The chlor-alkali process is one of the largest volume industrial processes, producing chlorine, hydrogen, and sodium hydroxide from brine. The Hall-Héroult process made aluminum affordable. Before 1886, aluminum was more expensive than silver. When multiple species can react at an electrode, competition occurs. The ease of discharge depends on the standard electrode potential. The more positive the reduction potential, the more easily the species is reduced. At the cathode, copper 2+ and silver ions deposit readily, while sodium and potassium ions cannot be deposited from aqueous solution because water reduction to hydrogen gas occurs first. At the anode, the overpotential for oxygen evolution is high on many electrodes, allowing chloride oxidation to precede water oxidation in concentrated brine. The chloralkali process uses 3 cell designs. The membrane cell uses an ion exchange membrane and is the modern standard. The older diaphragm cell uses an asbestos diaphragm. The mercury cell has been largely phased out due to environmental concerns. Water electrolysis produces green hydrogen, though currently only 4% of global hydrogen comes from this method. The Hall-Héroult process for aluminum consumes enormous amounts of electricity. A single plant may use as much power as a small city. The down cell produces sodium metal and chlorine. Let us test your knowledge with a quick quiz. Which statement about an electrolytic cell is correct? Option A, the cathode is positive and oxidation occurs there. Option B, the anode is positive and oxidation occurs there. Option C, the anode is negative and reduction occurs there. Option D, it produces electricity from a spontaneous reaction. Take a moment to think about your answer. The correct answer will be revealed shortly. Next question. What is the value of the Faraday constant? Option A, 6.022 times 10 to the 23 coulombs per mole. Option B, 96,485 coulombs per mole. Option C, 1.602 times 10 to the negative 19 coulombs per mole. Option D, 8.314 joules per mole per Kelvin. Think carefully, and the correct answer will appear. Quiz question 3. What products are formed when molten NaCl undergoes electrolysis? Option A, Na solid and Cl2 gas. Option B, NaOH and H2. Option C, NaCO and H2O. Option D, NH and ClO2. Think about the half reactions and choose your answer. Quiz question 4. Which is the correct cathode half reaction during the electrolysis of water? Option A. 2H2O yields O2 plus 4H plus 4 electrons. Option B. 2H2O plus 2 electrons yields H2 plus 2OH minus. Option C. H2 yields 2H plus 2 electrons. Option D. O2 plus 4H plus 4 electrons yields 2H2O. Remember, reduction occurs at the cathode. Final quiz question. Which ion cannot be deposited by electrolysis from an aqueous solution? Option A, Cu2 plus. Option B, Ag plus. Option C, Na plus. Option D, Zn2 plus. Consider the reduction potentials and the selective discharge rules to find the answer. Now we work through problem 1. A current of 2.50 amperes is passed through a copper sulfate solution for 30.0 minutes. What mass of copper metal is deposited on the cathode? Given that the molar mass of copper is 63.55 grams per mole and the Faraday constant is 96,485 coulombs per mole. Step 1. Identify the half reaction. Copper 2 plus 2 electrons yields copper metal, so the number of electrons is 2. The current is 2.50 amperes. Time is 30 minutes times 60 seconds per minute equals 1800 seconds. Step 2. Calculate the total charge passed. Q equals E times T. Equals Faraday del 50 times, 1800 equals 4500 coulombs. Step 3. Apply Faraday's equation. Mass equals Q times M divided by F times V. That is 4,500 times 63.55 divided by 96,485 times 2. This gives 285,975 divided by 192,970. The answer is 1.48 grams of copper metal deposited on the cathode. Problem 2. A silver plating operation deposits 5.40 grams of silver onto a metal surface in 45 minutes. What current is required? The molar mass of silver is 107.87 grams per mole. Step 1. The half reaction is silver plus 1 electron yields silver metal, so V equals 1. Mass is 5.40 grams, time is 45 minutes times 60 equals 2,700 seconds. Step 2. Rearrange the Faraday equation to solve for current. I equals M times F times V divided by T times M. Step 3. Substitute the values. I equals 5.40 times 96,485 times 1 divided by 2700 times 107.87. This equals 521,019 divided by 291,249. The answer is 1.79 amperes. Problem 3. How many minutes are required to plate 15 grams of chromium from a chromium 3 sulfate solution with a current of 8 amperes? The molar mass of chromium is 52 grams per mole. Step 1. The half reaction is chromium 3 plus 3 electrons yields chromium metal. The number of electrons is 3. Mass is 15 grams. Current is 8 amperes. Step 2. Rearrange to solve for time. T equals m times F times V divided by I times m. T equals 15 times 96,485 times 3 divided by 8 times 52. That is 4,341,825 divided by 416, which equals 10,437 seconds. Step 3. Convert to minutes. 10,437 divided by 60 gives 174 minutes, which is 2.9 hours. Problem 4. Water electrolysis produces hydrogen and oxygen gas. A current of 5 amperes is passed through acidified water for 1 hour. At STP, where 1 mole occupies 22.4 liters, what volume of each gas is produced? Step 1. Write the half reactions. At the cathode, 2H2O plus 2 electrons yields H2 plus 2 OH minus, so V equals 2 per hydrogen molecule. At the anode, 2H2O yields O2 plus 4H plus 4 electrons, so V equals 4 per oxygen molecule. Step 2. Calculate total charge. Q equals 5 times 3,600 equals 18,000 coulombs. Step 3. Find moles of hydrogen. N equals Q divided by F times V. 18,000 divided by 96,485 times 2 equals 0.0933 moles. Volume of hydrogen is 0.0933 times 22.4 equals 2.09 liters. Step 4. Find moles of oxygen. N equals 18,000 divided by 96,485 times 4 equals 0.0466 moles. Volume of oxygen is 0.0466 times 22.4 equals 1.04 liters. The volume ratio of hydrogen to oxygen is 2 to 1. Problem 5. An industrial chloralkali cell runs at 150 kiloamperes for 24 hours. What mass of chlorine gas is produced? The molar mass of Cl2 is 70.90 grams per mole. Step 1. The half reaction is 2Cl- yields Cl2 plus 2 electrons, so V equals 2 per chlorine molecule. Current is 150,000 amperes, and time is 24 times 3,600 equals 86,400 seconds. Step 2. Calculate total charge. Q equals 150,000 times 86,400 equals 1.296 times 10 to the 10 coulombs. Step 3. Apply Faraday's law. Mass equals Q times M divided by F times V. That is 1.296 times 10 to the 10 times 70.90 divided by 96,485 times 2. This equals 9.189 times 10 to the 11 divided by 192,970. The answer is 4.76 times 10 to the 6 grams, which is 4.76 tons of chlorine gas. Let us pull everything together. Electrolytic cells use electrical energy to drive non-spontaneous redox reactions. The external DC source forces electrons to flow. Oxidation occurs at the positive anode. Reduction occurs at the negative cathode. Faraday's laws give us the quantitative framework. The mass deposited or liberated depends on charge, molar mass, and the number of electrons involved. The Faraday constant of 96,485 coulombs per mole relates charge to moles of electrons. Selective discharge rules tell us which species react in aqueous solutions based on their standard reduction potentials. From the downcell for sodium production to the Hall-Héroult process for aluminum, from electroplating jewelry to producing green hydrogen, electrolysis is essential to modern technology. Thank you for learning about electrolytic cells and electrolysis.